This is the Pearson Edexcel, of course, chemistry for Unit 6 for May, June 2021. Of course, this paper was done in May. There was no official exam during that time, so I can say May, June 2021 or summer 2021. This is, of course, 50 marks. I will go straight to the first question. This says, this question is about compounds containing the ammonium ion. Of course, the ammonium ion, everybody knows, looks like that. So ammonium vanadate, this one here, is a white solid. When excess dilute sulfuric acid is added to an aqueous solution of ammonium vanadate, here we see there is one ion converted into this other ion. And then they say, of course, this is vanadium 5 of vanadium 5 being converted to another, of course, version of vanadium. So write an ionic equation for the conversion of that ion to that ion on the addition of dilute sulfuric acid. Step symbols are not required. Now here we see, remember, this is addition of an acid. So an acid is added to this, which is in +5 oxidation state. Let me see, a +5 oxidation state. And this one here is still in +5 oxidation state. So we get that water. Again, this is not redox because they are still in the same oxidation state. The first question says, of course, this one is okay. Then the other. Before actually we go on, if you write a half equation, like in this case, we know we have VO3 this side and the other side we have VO2 plus. One thing we know is they're adding hydrogen here. However, the other side we do not know. You always add water to balance the oxygen deficit or from the other side. Here we have 3 oxygens on this side. Here we have 2. So add water to balance the oxygens, meaning now the oxygens are balanced, and then balance the hydrogen ions to ensure that everything is fully balanced. So that's how you write this kind of equation or half equation. So in this case, actually, there are no electrons that are going on. So this kind of equation, we can just balance it like that. So part 2 says, state the color of the acidified solution of ammonium vanadate. Of course, it's going to be yellow. You guys know the changes in oxidation state of vanadium. We have vanadium 5, vanadium 4, vanadium 3, and vanadium 2. They're all going to have different oxidation state. So part 3 says, a student added zinc metal to an acidified solution of ammonium vanadate 5. Please remember, zinc is a good reducing agent. Every time you say zinc, add it to something, maybe there is a redox reaction somewhere. No, zinc is acting as a reducing agent in most times. So that zinc reduced the vanadium in a series of reactions. A student suggested that the sequence of colors observed could be explained by the presence of vanadium species shown below. So the student thinks that the starting color goes to green, then we go to blue, then we go to green and go to violet. So this student thought, because it's going to be green, of course we know vanadium 3, yes, and then it's going to be that color. The student thought that every time we see a green color, it's going to be vanadium 3. We see violet, is going to be, of course, vanadium 2. But actually, the green color could be, or in this case, most of the time, this green color here could be a mixture of a yellow and a blue color, not necessarily vanadium 3. So here they say, explain whether or not the student is correct. Refer to the oxidation state of vanadium and account for each color in the sequence. So I said vanadium 5, oxidation state, vanadium in oxidation state +5 is yellow. That is correct. +4 is going to be blue. And then we have, of course, yellow, blue. And then we know that +3 is going to be green. And then +2 is going to be violet. So here we see the initial green is due to a mixture of these two, of course. The two are going to create a green color. We have, so the green color is going to appear due to a mixture of this color in this oxidation state and that oxidation state. That is the explanation that we're looking for. Next, part IV says, when the mixture obtained at the end of the sequence of A111 is filtered, the filtrate changes color from violet to green on standing. Now, changing color from violet to green on standing, it means there is further oxidation. Again, from back here, we see violet is going to be vanadium 2 and green is going to be vanadium 3. So it means it's changing from V2 plus to V3 plus, and they have explained, they've written to you on standing. Every time they say on standing, it means there is oxidation by oxygen in the air. So here they say, suggest an explanation for these observations. Oxidation of vanadium 2 to vanadium 2 basically to vanadium 3, that is 1 mark, and then by oxygen However, oxygen is not strong enough. Here, the question said no further change occurs. You have to explain all that. We know that it changes from violet to green because this has been oxidized to that by oxygen in the air. However, why doesn't it create other colors of higher oxidation states of vanadium? It is because oxygen is not strong enough oxidizing agent to cause vanadium-3 to be oxidized to higher oxidation states. Next part says ammonium tetrachlorocuprite dihydrate, which is basically that, is a blue-green solid. When ammonium tetrachlorocuprite dihydrate is dissolved in water, a blue-green solution T forms, suggests the formula of two complex ions present in here. So it could be because the tetrachlorocuprite is released, that is why we see maybe a blue-green, or it could be a combination of these. But here, of course, they asked for any possible ions. You can give the two of these. Next, state how the color of T would change on the addition of excess concentrated hydrochloric acid. Excess concentrated hydrochloric acid to T is going to convert the blue color to green and then to yellow. The reason for this is, of course, the copper H2O6 is going to be converted, of course, to CuCl. This is going to be 4, 2 minus. This is going to be, of course, 2 plus. This is going to be blue. This is blue. And this is yellow. So this green color is due to the blue and yellow being in 1 plus. And then we can see something that looks green. Next, describe what will be observed on the addition of an aqueous sodium hydroxide to T. Sodium hydroxide addition to T would cause the formation of a blue precipitate of copper 2 hydroxide. And then next, when the mixture of B from B3 is warmed, a gas is evolved. Give a test to identify the gas, stating the positive result. If, of course, the mixture from 3, if it's warmed, of course, here you have something. You have added sodium hydroxide, and then you are to the sample. Remember, this sample contained this whole thing. When you dissolve it in water, it means the ammonium ions are also dissolved in water. So it means in that sample we have some ammonium ions in there. Now to that you add sodium hydroxide. When you add sodium hydroxide and then you warm, again here they say that you warm, it means warming. The addition of ammonium and sodium hydroxide creates ammonia but ammonia is going to be, most of it is going to be dissolved. However, when we warm, this gas comes off, creating a gas that is which is ammonia, and then we test it using damp red litmus paper. Or you could use concentrated HCl producing hydrogen chloride gas, which could form a white smoke when it comes in contact with, of course, ammonia gas. I will go to the next part of the question, which is the last part of question 1. A white solid with a slight vinegar-like smell. Vinegar-like smell means kind of organic acid smell. Contains ammonium ions and an ion represented by Y minus. The smell of vinegar intensifies on the addition of a few drops of concentrated sulfuric acid to an aqueous solution of NH4Y. On subsequent addition of a few drops of ethanol and heating the mixture, the smell of vinegar is replaced by a sweet fruity smell, meaning this is an ester. So this was an organic acid converted to an ester. It means whatever they've added could be an alcohol. So here they say, explain how all this information can be used to identify Y minus. So I say intensification of vinegar smell on addition of H2SO4 shows formation of ethanoic acid. Formation of ethanoic acid, of course. However, formation of sweet fruit smell due to the formation of an ester, and Y minus could have been this. So basically, it's like an ester or some kind of product that is made. So Y minus is going to be ethanoate, an ion. And again, you remember when we combine a carboxylic acid and an alcohol to form an ester, there should be an acid that is being added. So, yep, an acid could do that as well. But if you can see here, the sweet smell is due to the ester. And then here we know that this is vinegar-like smell is going to be ethanoic acid. When you add a few drops of ethanol, which is the alcohol, and then you heat, we're going to produce an ester. So this brings us to the end of question 1. Let's continue on to this question. Concerns the laboratory preparation of tetraamine copper 2 sulfate 1 water, which is basically that. The procedure says weigh between 2.1 gram to 2.3 grams of hydrated copper to sulfate, which is basically that, in a boiling tube, and add 8 centimeters cubed of distilled water and place the boiling tube in a hot water bath. Stir the mixture until the crystals have dissolved. Step 2. Working in a fume cupboard, of course this is for safety reasons, slowly pour 5 centimeters cubed of concentrated aqueous ammonia into the boiling tube. Stir until a clear solution is formed. Measure 12 centimeters of ethanol into 100 centimeters cubed conical flask. We are measuring 12. And add contents of the boiling tube from step 2. Stopper the flask and swirl the contents before placing the flask in an ice bath. Allow the mixture to stand until the crystals of this are formed. Then, filter the crystals obtained in step 3 under reduced pressure using a Proton funnel and flask. Pour 5 centimeters cubed of cold ethanol. Now, this is going to be the solvent. Over the crystals in a funnel. We are washing, basically, this is the washing process. We are washing the solvent. Then use a spatula, transfer the crystals to a filter paper on a wash glass. Press the second piece of filter paper on the crystals to dry them as much as possible, and then transfer the crystals to a dry pre-weighed sample of sample bottle and weigh. Give a reason why the measuring cylinder is more suitable than a graduated pipette for measuring the distilled water. Now, the distilled water measuring cylinder is basically going to be quicker at doing this. So it's going to be very quick, because when you're doing the experiment, when you do with a pipette, it's going to take longer. So it's going to be fast enough. Next question says, give the color of the solution at the end of step 2. The end of step 2, let's see. Step 2, they said, working in a fume cupboard, slowly pour 5 centimeters cubed of concentrated ammonia into a boiling tube and stir. Here we're going to see dark blue crystals basically are going to form, because this is going to be copper in here. Remember, copper in ammonia, we form a deep blue solution when you have copper in solution. So here we expect, if they are crystals, to form dark blue crystals or dark blue. Next part says, give the reason why step 2 should be carried out in a fume cupboard is because of ammonia gas being toxic. Give the reason why the addition of ethanol in step 3 results in the precipitation of crystals of copper, of course, of the sample they have produced, or the crystals they produced. Here we see that the crystals are going to be less soluble in copper and less soluble in, of course, aqueous ethanol. Aqueous ethanol is a solvent they're trying to use, but probably the crystals are going to be kind of, if you heated the ethanol, maybe solubility could be higher. But in this case, we see addition of this ethanol causes the crystals to form, so it's going to be less soluble within the ethanol. The next part says, draw a Labo diagram of the apparatus used to filter the crystals under reduced pressure in step 4. This whole thing is filtration under reduced pressure. However, the Boschner funnel is that funnel here we are using to filter. So you have to show that the opening here, where the part that leads to the vacuum pump, and then the filter paper has to be laid flat, basically laying flat within the funnel. Next part says that the purpose of ethanol in step 5. Again, we already saw ethanol was a solvent. So in step 5, because ethanol is not dissolving, when it's cold, it's not dissolving the sample, it's there to dissolve the impurities. That is why it was used for washing. It was used to wash the crystals. It was used to wash the crystals during the filtration, basically. And then the next part says, give a reason why ethanol is cold. Of course, it's cold to minimize. You do not want the crystals to dissolve in the ethanol. So we want only a minimum amount of that, which dissolves in the cold ethanol. So we do not want a lot of it to be able to dissolve. So you add less ethanol, minimum amount, to prevent, of course, solubility. Again, we have already said, ethanol, the sample can dissolve in ethanol, but of course it has less solubility. If it has less solubility, it means if it's less, solubility is going to be less. If you use a higher volume, there is a chance that it's going to dissolve more and more, and we do not want to lose the sample we have just prepared. The next part says, starting with 2.17 grams of course, copper sulfate, with 5 moles of water, and using excess ammonia, a student obtained 2.45 grams of product. Of course, this is easy. This is what you reacted with, the copper sulfate, hydrated copper sulfate with ammonia to get that, and then water. So we know this is the mass, and this is the actual yield. We're going to work to find the number of moles. We know the molar mass of the hydrated copper sulfate is that, and the molar mass of the product is going to be that. So we're going to work backwards. We'll begin with number of moles of copper sulfate by using the mass we have and the molar mass of copper sulfate to find those number of moles. And we will use the mole ratio, which is basically 1:1, meaning the moles of the product are going to be exactly similar to the moles of the copper sulfate that reacted. Now that we know this, we multiply the number of moles and the molar mass to find the mass. This is going to be the theoretical yield. So we know that percentage yield is equal to actual yield divided by theoretical yield times 100. The actual yield is what was generated, and then the theoretical yield is what we have got, times 100, and this gives us a more than 100%, which is 119%. That is higher than 100, and it's because maybe we have overestimated whatever they measured here. The actual mass of the sample could be more than actually it was. Maybe the sample was not dry enough, so we need to know. Part 2 says, suggest a reason why the apparent percentage yield in this preparation is often greater than 100%. The reason for this is because, of course, the crystals are wet. There is no way the actual yield can be higher than the theoretical. The only reason is because this was the crystals were wet and they had water present within them. This brings us to the end of question 2. Let's continue to question 3.
It says this question is about the identification of 6 organic compounds. So here we have 6 organic compounds, and I already positioned in the carbons to help us make it easier. So let me position in the hydrogen so that we can be able to see the different proton environments as well. Position them in there. Give me some time. I'm trying to position in the hydrogen so that it's easier for us to see in case we have to explain about the proton environments as well. So I already saw this part here has, if I use a highlighter here we have 1, 2, and 3. So here we have 1, 2, 3 carbons. However, we also have 3 carbon environments, 3 carbon-13 environments, because these environments are all not the same. Here we have we have 1 here, the second, the third, and the fourth. And of course, there are 4 carbon environments. This is carbon-13 NMR. Here we have this environment, which is going to be identical to that environment, this environment, which is identical to that, and then this, which is unique. So we have 3 proton environments, hydrogen environments, 3 carbon environments. So when we come here to E, we have that and that, because this is similar to that, this and that are identical. So we have 1 carbon environment. And lastly, here we have that, and that. These are all different environments, so they end up there are 4. The first question says, from A, B, C, D, E, and F, identify the compounds with 1, the fewest peaks in the carbon-13 NMR. We have already seen that this is going to have the fewest peaks because the environments are identical, so it comes out as 1 peak. So it's going to be compound E. And next we see the most peaks in low-resolution proton NMR spectrum. So the most peaks, here we are looking at the proton NMR. If we try to see, here we're going to have 3, let me see, we have 1, 2, 3, and 4. So we have 4 proton environments. Okay, so proton environments. Here we have 1, which is identical to that, and that which is identical to that. So here we have 2 proton environments. And here, environments, I'll say environments. And above here, I can say environments as well. Okay, so when we come to this one, we have 1, we have a second, and a third. 3 proton environments. Here we have 1 and 2. These are actually identical, so we can say, of course, it's 1 proton environment because it's the same. And then here we have 1, which is identical to that. So, of course, 1 proton environment. And here we see we have that. We have that. Those are going to be 2 proton environments. So in case we see this one has the most proton environment, so compound B ends up being the one with the most peaks in the low resolution NMR, proton NMR. So the next part says 3 peaks with relative peak area 3 to 2 to 1 in low resolution proton NMR. Let me use another color. Low resolution. So they want us to find a 3 to 2 to 1. Of course, it's this one. You can see there are 3 peaks here, there are 2 peaks here, and there are 3 peaks here. So it's going to be compound F. And here we see the next part says 1 triplet, 1 quartet. A triplet, it means it's a hydrogen environment closer to some environment that has 2 hydrogens, and here this is an environment closer to another environment that has 3 peaks. So we are looking for this is going to be an environment that has some peaks closer. Let's see. We have that, which is identical to that, and in this environment we have 3 peaks. However, this environment is closer to one environment with 2 peaks, so this is going to be a triplet. However, this environment here is closer to 3 peaks, and therefore it's going to be a quartet. This environment and that are both quartet, while this and that are both what we call triplet. So it ends up being compound D, being the answer here. So part B says for each of the following pairs, give 1 chemical test, not including indicators that could be used to distinguish the compounds. So here we say identify reagents and give the reasons for each. A and B, this is the carboxylic acid as well as the methyl ketone. You can see this is the carboxylic group and that is the methyl ketone. Here we have an alcohol and of course a ketone. So we can use acidified potassium dichromate, and in this case the carboxylic acid will have no observable change and the ketone will have no observable change. However, the alcohol, primary alcohol, will cause a color change from orange to green due to its oxidation. And or we could use sodium carbonate, because there is a carboxylic group. The sodium carbonate will result into effervescence from the carboxylic acid. The next part we have, of course, the methyl ketone here and the methyl ketone here. This is a methyl ketone, the whole thing like that, and that's methyl ketone. This one here is just a ketone. How can we distinguish the two? Methyl ketones can be confirmed using the iodoform test. This, you will warm sodium hydroxide with iodine, the iodoform test, and the positive result is yellow precipitate being formed with C and D will have no observable change. Next part says, liquids boil at a temperature at which their vapor pressure is equal to atmospheric pressure. So they say the apparatus shown below was used to determine the boiling temperature of A, which is a liquid at room temperature and pressure and has the boiling temperature in the range of 120 to 180. So we look at the setup, and then they say place a capillary tube sealed at one end and with the other end open facing, of course, the open end facing down into 0.5 centimeters cubed of compound A in a micro test tube. Attach the micro test tube to a thermometer with a rubber band and clamp the micro test tube and the thermometer in the mineral oil, making sure neither test tube nor thermometer bulb is in contact with the glass walls of the fuel tube. Move a small Bunsen flame back and forth along the lower part of the side arm of the fuel tube. An initial stream of bubbles will come from the open end of the capillary tube. Continue heating until a rapid and continuous stream of bubbles comes from the capillary tube. Stop heating and record the temperature as soon as the compound A is drawn up in the capillary tube. So the first question here says, state what causes the initial stream of bubbles from the capillary tube in step 3. It's trapped air. Trapped air is going to expand on initial heating, and that will come out of the capillary tube, leading to kind of bubbles coming out. Part B suggests why the side arm of the fuel tube is heated rather than at point X on the diagram. Taking you back here, heating at point X will create direct heat towards the thermometer, and therefore we're going to detect false temperature. However, when we heat here, it allows for heat to be evenly distributed before it's detected by the thermometer from both sides, that way as well as this way. So it means we are going to be detecting accurate temperature. So even distribution of heat is going to be allowed. Next part suggests why mineral oil and not water is used in the fuel tube. You know, water boils at 100 degrees.
yet the sample is going to boil at 120 to 180. This is way higher than the boiling temperature of water, so we need to use mineral oil whose temperature is actually higher than that of water to allow, or actually whose boiling temperature is higher than the boiling temperature of the sample we are trying to boil. Next phase suggests why the result obtained when using this apparatus is on different days may not be the same, even when no mistakes are made in carrying out the experiment. Again, I'm going to take you back to the beginning of this question slowly. If you see this statement here, they say liquids boil at the temperature at which their vapor pressure is equal to the atmospheric pressure. Now we know atmospheric pressure is going to be different on different days, and that means the similar liquids are going to boil at different temperatures on different days due to the difference in atmospheric pressure. So that is why we can see. So I say since boiling temperature depends on atmospheric pressure is variable on different days. That is why we have that. One of the compounds A, B, C, D, E, or AF was analyzed. To determine its empirical formula, 1.57 grams of this compound was burned completely, and the combustion product was passed through the apparatus. So if they say burned completely, it means only carbon dioxide and water was produced, except the excess oxygen, but the two things are going to be carbon dioxide and water. So they're going to say solid M absorbs water and increase the mass by this. So this should be the mass of water generated. Anything that absorbs water should be anhydrous, so it can be anhydrous calcium chloride, anhydrous calcium sulfate, anhydrous magnesium sulfate, or you could even use the silica gel. Then part N, solid N absorbs carbon dioxide and increased in mass by 3.14. This is the mass of carbon dioxide produced. So here it could be potassium hydroxide, sodium hydroxide, calcium hydroxide, or even soda lime. So when they say identify solid M and N, solid M could be anhydrous calcium chloride, and solid N could be soda lime, which looks like that. So I will go to the next part. Calculate the empirical formula of the compound using the data given. You must show you're working. From the data, we have the mass of water and the mass of carbon dioxide. But we know in each water molecule, the hydrogen is 2 out of 18. So 2 over 18 times the mass of water gives us the mass of hydrogen. And 12 out of 44, remember carbon dioxide is like this, carbon is 12, the whole thing is 44. So 12 out of 44 times the mass of carbon dioxide gives us the mass of carbon. Now here, since we know the mass of the sample originally, so add the mass of hydrogen plus the mass of carbon, subtract them from the original sample, gives you the mass of oxygen that was contained in the original sample. So here they want us to determine the empirical formula. You position carbon, hydrogen, and oxygen, position their individual masses, and divide by their atomic mass to find the number of moles of each. And then we divide through by the smallest number of moles to find the whole number ratio. And then use this whole number ratio to find the empirical formula, which is carbon 2, hydrogen 4, oxygen. That is the empirical formula. So continuing to the next, they say the mass spectrum of compound is shown. So here we have a mass spectrum, and they say deduce the relative molecular mass of the compound using the mass spectrum. When we use the mass spectrum, we look at the farthest peak, which is going to be here. In this case, it's at 88. So at 88, it means since the molecular ion peak has a mass to charge of 88, so the molecular mass of this sample should be 88 as well. Looking at that peak there, which is at 88, mass to charge. Next, deduce the molecular formula of the compound using your answer. Now, previously, you remember we had carbon 4, hydrogen 8, oxygen. Again, to take you back, it was carbon 2, hydrogen 4, oxygen. Okay. If we had carbon 2, hydrogen 4, oxygen, and we know this times N is equal to 88, it means our N, remember this is carbon 2 is 24 plus 4 hydrogens and 16. This creates 44. So 44N is equal to 88. N should be 2, and therefore multiply everything by 2, creating a carbon 4, hydrogen 8, oxygen 2. That is the molecular formula, and the empirical formula was that. So continuing to the next part. So the next part says, deduce the identity of the compound using your answer to D4 and the fragmentation pattern of the mass spectrum and justify your answer. So again, remember the things we had for the mass spectra, for the molar mass, we have found out to be carbon. Again, let me take you back a bit from the previous page. The previous page, because we got mass to charge, I think it was 88, and carbon 4, hydrogen 8, oxygen 2. So this has 3 carbons, so that is out. This has 2 carbons, it's out. We are looking for something with 4 carbons. This has 5 carbons, it's out. So here, when we look at, let me see, we look at this one here, it has 2 carbons, so it's going to be out. We remain with, let me see this one, 1, 2, 3, 4. It has 4 carbons, but it does not have a peak at 29. Again, looking here, we have a peak at 29 that is going to be significant. So any of the things that has a peak at 29, and this is F, so it tells you compound F, because it has a molecular mass of 88, and it can form a fragment at with mass to charge 29. This is the end of this paper. This is a Unit 6 chemistry paper for May, June. I'll see you in our next paper. Thank you for being with us.